Hi everyone. Today we're going to be covering a new topic called separable differential equations. Now, we've been working with differential equations already, and if you remember back, we said we always recognize a differential equation by this dy dx. So what's happening is that we're being given a derivative, and we're trying to find the function that has that derivative. Now, the difference today is, you'll notice, today our differential equation is expressed in terms of both x and y. So if I have a differential equation, dy dx, that has an x and a y on the right side, that's when we know we're going to have to do what's called separating our differential equation. So we're going to go through some steps for solving, and then we'll go through a few examples because this can get a little bit complex. So sometimes we have a differential equation that is expressed in terms of both x and y. So here's how we're going to solve, and we'll go through it with this one, and then like I said, we'll do a few more examples. So the first thing we need to do is separate the variables by bringing all of the y terms to one side and all of the x terms to the other side. So it means anything that has a y, I want to move over to the left with my dy. Anything that has an x is going to go on the right with my dx. So here, obviously, we need to move this y over to the other side. So I'm going to divide both sides by y. So I'm going to have dy over y. My 3x is going to stay on the right side, and just like before, I'm going to multiply by dx. So that multiplying by dx hasn't changed, it's just now we have to move anything with a y over to the left-hand side. So now I have everything with y on the left, everything with x on the right. So now we're going to find the antiderivative of both sides with respect to its variable. So just like before, we're going to integrate both sides. So now we have to be careful because we're not just going to get y equals on the left side. We have to actually consider the antiderivative here. Remember, the integral of dy over y is the same as the integral of 1 over y times dy. So its antiderivative is the natural log of the absolute value of y. On my right-hand side, I'm going to use my power rule. This really has an exponent of 1. So if I add 1, that's going to be x squared. And then I need to divide by that new exponent. So I still have my 3, and I'm going to divide by 2. Now, just like before, only one side is going to need that plus c. Because if we had a plus c on both sides, ultimately we would combine them into a single constant. And this c, remember, is just some generic constant. So for step 3, let's fill that in. Only one side needs a plus c, because they would be combined into a constant. Now, a big step that is missing here, so let's put this in. The next thing we need to do is to solve, can we even see that? Solve for y. We have to get y alone. Because remember, we're looking for a function that has this as its derivative. So this is a little bit tricky. I have y as the argument of the natural log, and I have to get it out of there. So I know to do that, I need to exponentiate both sides. So I'm going to take e to the natural log of the absolute value of y, and I'm going to have e to the 3/2 x squared plus c. Now, here's where we have to use properties of exponents. I know if I have e to the 3/2 x squared plus c, that's the same thing as e to the 3/2 x squared times e to the c. Now, again, remember c is some generic constant. If I take e to the c, that's still going to give me a constant value. So I'm going to express that e to the c as just a constant value c. I'm going to pull it out front. So this e to the c just becomes our generic constant c. So I have c times e to the 3/2 x squared. Now, When I take e to the natural log of the absolute value of y, I know e and natural log are inverses, so I just end up with the absolute value of y. So now we've almost got y all by itself. If I drop the absolute value, I know that y is equal to either positive or negative c times e to the 3/2 x squared. But again, that positive or negative c is just some constant. So we're just going to express that as c times e to the 3/2 x squared. And that is going to be our answer. And remember, this is what we would call a general solution, because we weren't given any initial condition to find a specific solution. Now, for step 4, it says make sure to specify the domain of the solution, and we'll talk about that with the next example. Okay, so let's look at number 1. Now, you'll notice here with number 1, I am given an initial condition. So here we're not going to be looking for the general solution. We're going to be looking for that particular solution. So that means we're going to be using this information to solve for c. So we start out just the same. I'm going to go ahead and recopy this problem. So I have dy dx equals the quantity x times y squared. Now, if I'm going to separate my x and y, the first thing I need to do is expand this, make this x squared times y squared. So now I can easily separate my variables. So I'm going to divide by y squared. So I have dy over y squared. And now I'm going to multiply by dx. So now I've separated my variables. Once we've separated, we're going to integrate both sides with respect to their variable. So this is y to the negative 2. So if I add 1, I'm going to have y to the negative 1. Divide by negative 1. I'm going to get a negative 1 over y. That's going to be equal to, over here, I'm going to have x cubed over 3, and I have a plus c. Now at this point, I'm going to take this information that I had up here and use it to solve for c. So when y is 1, I'm going to have negative 1 over 1 equals, x was 1, so I have 1/3 plus c. So now if I subtract 1/3 from both sides, I'm going to get c is equal to negative 4/3. So now I'm going to take this c and I'm going to plug it into my answer here. So now I have negative 1 over y equals x cubed over 3 minus 4 over 3. I'm going to go ahead and combine this into a single fraction, so x cubed minus 4 over 3. So now we're getting closer, but now we have to solve for y, get that all by itself. So the first thing I'm going to do is I'm going to multiply by a negative 1, so I can just make it 1 over y. And so that's going to change my signs here, so I'll have 4 minus x cubed over 3. And now to solve, to get y by itself, I can just take the reciprocal of both fractions. So y is going to be equal to 3 over 4 minus x cubed. Now, we said above that we needed to make sure to specify the domain of the solution. So here's what we know. For my function here, I know that 4 minus x cubed cannot be equal to 0. Right? So I know that x can't be equal to the cube root of 4. So I know that this function has a domain of negative infinity to negative cube root of 4 and cube root of 4 to infinity. Now, here's the trick. I am finding the solution when x is 1 and y is 1. Right? So my point, 1, 1, fits into this piece of the domain. So again, I look back and it said to find the solution when y is 1 and x is 1. I know that point lies in this piece of the domain. So when we specify, let's fix that there. Okay, let's jump back a second and clean this up. Since x is not equal to the cube root of 4, it should be negative infinity to positive cube root of 4 union cube root of 4 infinity. So actually my point 1, 1 lies in this piece of the domain. So when we specify our domain for our solution is y equals 3 over 4 minus x cubed, and we're going to specify that piece of the domain that contains that point. So our domain is going to be from negative infinity to cube root of 4. Okay, and so I'm going to make a little note here. So we know this solution is valid for the continuous piece of the function that passes through the given point. So again, that's why we specify this portion of the domain. All right, let's go on and try a few more examples. Okay, for number 2, again, we have a differential equation. It's expressed in terms of x and y. And again, since we're given an initial condition, we're going to find a particular solution, which means I should not have a plus c in my answer. So the first thing we're going to do is we're going to separate our variables. So I'm going to divide by y, dy over y equals 2x times dx. We're going to integrate both sides. So on the left, I'm going to get the natural log of the absolute value of y. And on the right, I have x squared plus c. Okay, so I'm going to go ahead and solve for c at this point. So now I know y is 3, so I have natural log of 3 equals x is 0, so 0 plus c. So c is equal to the natural log of 3. So now I have the natural log of the absolute value of y equals x squared plus the natural log of 3. So now we have a situation like we did on the first side where I have a natural log and I need to isolate the y. So we're just going to do e to the natural log of the absolute value of y equals e to the x squared plus ln 3. Again, here's where I have to remember my properties of exponents. I know this is equal to e to the x squared times e to the natural log of 3. So now e to the natural log of y, those cancel each other out. So I have the absolute value of y equals e to the natural log of 3, I know is just 3. So I have 3 times e to the x squared. So now, if I want to drop those absolute values, what I really have is y equals plus or minus 3 times e to the x squared. And so we have to decide whether we need a plus or a minus. So here's where I'm going to make a note. What we need to do is we need to look at the initial condition to determine the sign. Okay, and that's going to be really important. So here's what I mean by that. I'm going to take my function and I'm going to plug in my value of x, which we said was 0. So if I have e to the x squared, that's just going to be e to the 0. E to the 0 is going to give me a 1. Now, I want my y value to be 3. So if I have a positive 1, the only way to get a positive value of 3 for y is if this is a positive value. So my initial condition tells me that my answer should be positive. So my answer is y equals positive 3 times e to the x squared. And that's my answer. Now, in terms of domain, our domain is all reals, so we don't have to specify a specific piece for this problem. All right, one last one for today, for tonight, I guess. All right, here we go. Again, I recognize I have a differential equation because I see dy dx, and I have it expressed in terms of x and y. So we're going to separate our variables. So let's see, I'm going to multiply this time by e to the 2y. So I have e to the 2y dy equals x squared dx. And I'm going to integrate both sides. Now, I know the derivative of e to the x is just e to the x. So the antiderivative of this is going to be e to the 2y. But I know taking that derivative would multiply this by a 2. Since I don't have a 2 in my integral, I need to divide by 2. Now, we could have done a u substitution here, but for basic problems like this, I want us to start being able to just think through what that antiderivative would look like. So now on the other side, I have x cubed over 3 plus c. So I'm going to go ahead and multiply this to make it a little simpler. So I'm going to multiply by 2. So I'm going to have e to the 2y equals, now I'm going to have a 2/3 x cubed. And remember, we talked about this earlier in the video. If I multiply c times 2, I'm still just going to have a constant. So we're just going to express that as plus c. That's still just a constant value. So now I have to isolate my y. Since this is e to the 2y, I can do that, or start to do that, by taking the natural log of both sides. So the natural log of 2/3 x cubed plus c. And again, I should specify, since we don't have an initial condition here, we're just going to be getting a general solution. That's why we still have our plus c. Okay, so now natural log of e to the 2y is 2y equals the natural log of 2/3 x cubed plus c. And the last thing I'm going to do is divide by 2. So y equals the natural log of 2/3 x cubed plus c over 2. And that is our particular solution, or excuse me, general solution to this differential equation. Now, obviously, there is a lot going on in these problems, so I expect there will be questions. Just kind of hang in there, and we'll work through it when we're back in class.